is water, right? I don't know what the order is. Yeah.
Give me a second to share.
Okay, same thing. Let's go to the computational catalogs.
Yeah.
What are the 4 languages for what?
Really nice page.
There are 4 languages.
So water, English, Arabic,
and Chinese. Yeah.
What's the middle one?
Arabic, I think.
No, the one after
Greek.
English. Is that Greek?
Yeah, it's Greek.
Ah, okay, fair enough. And that's the Chinese symbols for water.
Yeah.
It's a really nice. Looks
It's a really nice page.
Okay.
International.
Yeah.
Actually, you did said that the Chinese letter shows the drops, like it's the drops.
Really?
Yeah.
Interesting.
The previous time we said that we should focus more on phase changing and try to depict that in the molecular level.
Yes.
So we try to focus more on this phenomenon and the relations between the particles, and how its state changes according to energy input or output variables. But we had a discussion also with Theo yesterday, and we had some thoughts about moving to a larger scale and maybe studying what we call water phenomena. We could say in a very simple way that we can understand water in different formations in nature, from the smaller scale to the larger scale, where different variables act its time and form this formation and act as variables in this formation. So we have what makes a gas and what makes a cloud, etc. So the formation factors, particle bonds between them, and which could be the simulation framework appropriate for each one. We had some general thoughts about the strategies in our simulation. So we could see water as a material, studying what phase change and basic water behaviors, and how we can augment this digital material. This could be the strategy 1. Strategy 2 is the fluid dynamics, so how water interacts with the environment, which would be equal to a fluid dynamic simulation. And then water as a container. So as we know, water contains life, contains sediments, contains mineral, microorganisms, planktons, many other things. And I think that this could be a combination of strategy 1 and strategy 2. At this point, as a first point in our research, we will focus in the first branch in strategy 1. So we studied the flocking simulation and the behavior of water phases. And we tried to draw a simulation analogy of the two systems together, which was quite, I don't know.
We made it as simple as we can so that we understand like how the behavior like the particles occur during each water phase. So our simulations are basically simple at this moment. If you can go on to the simulations, like we started to see how they behave in solid, how do they vibrate, the particles, and liquid, how the distance between them, and then like I think if we go to the next, we started to simulate going from the phase change from liquid to gas and see the behavior of these simulations on Maya.
How we can tweak actually the attraction forces and the collision forces. Mhm. So this was not very successful as an ice representation, but I think that this group of particles, like the smallest groups, seem to behave more than like a crystal, because they seem more, you can understand that the bonds between them are strong.
Mhm.
But in the larger population, you can't really see that.
Okay. So you're using collide scale, self-collide. That's fine. Point field. Self-attract. Okay.
And like we attempted also to mimic the crystallization phase from liquid to solid. I think this is not a good attempt, or like it's a simple attempt, but the logic of crystallization is having a structured and a very organized manner of the molecules and the bonds. Like in this one, it's very random.
So yeah, we tried to combine growth and the previous set of attributes that we set for solid, right?
Mhm.
And then we entered the field of flocking simulation. These are the basic rules.
We just studied at first the simple rules on Maya, like separately, so that we understand how this would, behave in Maya. And then, like we know that there are 3 rules: separation, cohesion.
How did you do alignment in Maya?
Yeah, this isn't flocking. It's just, like there is no, they're not actually trying to average. They're just colliding, right?
Yeah, like it was difficult to do flocking in Maya.
Yeah.
So we thought of dividing the rules for now, and then like try and
There's a flocking node in Maya, like that basically just simulates flocking. Like you can use that. It's just that it's not very hackable, unlike the particles.
the match one. It's
Sorry?
unmatched, right?
Yeah, there is the matched one. So that one is for flocking, and it will just flock. You can also add collisions to the objects if you want, like dynamics. And there's also a very old plugin that someone made that turns particles into flocks. So you can utilize some of the like the abilities of the particles, but you also add a node to them that is the flocking node, so they will behave as a flock. But you can also, do whatever you do with particles as well.
Okay. All right, but yeah, like that was interesting. But it's okay. Keep going.
So we were trying to like draw an analogy between like how we could use the flocking simulation into and the phase change of water.
Yeah.
And we introduced an attractor, which is it influences the alignment of or like trying to influence the alignment of the particles. So like if you replay the video, you can see that when they go towards the attractor, they're much closer. Like it mimics the strong bonds, which is the solid phase, and then when they're away from the attractor, they separate and become like a gas phase kind of simulation.
Yeah.
So yeah, what I'm trying to say here is we're trying to use the flocking simulation in Maya and draw the analogy between the flocking and the water phase.
Yeah, I can see that.
So it's just a simple study, yes, but like I don't know how. I don't know. How,
Fair enough.
yeah. And then we moved on to Unity.
Mm-hmm. Yeah, I see that. I know, keep going. Yeah. So yeah, I see where you guys are going. But yeah, I think there's a couple of fundamental things we should talk about. Yeah, like before we go into targets and stuff. So can you just quickly flick through your presentation just so I see what else you've done? So if there's anything, yeah. So targets, keep going, keep going. Yeah, keep going. No, I'm shaking my head if you can't see it. Let's not do L systems. Yeah, this is, yeah,
Go to
keep going.
page. Previous.
Okay, is this it?
Yeah.
Okay, I actually think you guys are in a really good direction. There's just some confusion. You're still, and I'll talk to Theo because I think he's adding to this confusion. You're still trying to think too much of trying to copy water, right? Like you're not abstracting water enough, but I think you've made really, really good steps forward. So yeah, I think iceberg, wave, cloud, it's great, but we have to start at the fundamental below all of this, right? So I think the concepts of scales of simulation is great. So steam, droplet, snowflake, keep that. I think it's a good idea. We can talk about that. But similar to the last team, you need your basic engine, right? The basic engine of generation. And I think flocking is the right direction. I think what you've done in Maya shows some of the stuff, but I think for your project, Maya's particle engine, unless you learn to hack it, is too limited. So given that you have the ability to edit flocking code now, and we can help you, I can help you with that, it's the right direction, right? So I'm just going to share my screen. So I had to open my tablet. Can you stop sharing, please? Yeah, thank you. I think what you guys have identified correctly is the concept of the particle or the agent in the flocking simulation, right? And for the sake of your project, it's the same thing, right? So let's call it the water agent, right? That's just a dot, right? And that dot has a vector to it, right? So the other thing you guys, why is it so weird? The other thing you guys figured out is this, attraction, cohesion. Well, figured out, like this is flocking, right? Attraction, cohesion, and separation, right? And in reality, can these three words apply to just one particle?
No.
Yeah, right. You have to. This is an interaction between at least two particles, right? So you have these two particles. What do you think attraction looks like in terms of this, right?
Mhm.
And what do you think separation looks like? Like this, right?
Yeah.
All right. So basically, this is similar to attraction, repulsion in Maya, right? It's exactly what you're doing inside Maya. Do you agree?
Yeah.
Okay. So you can already control that using the attraction and separation rules inside flocking, right? So does that make sense? Okay. Cohesion, I think, doesn't apply for you right now. I think we can run the simulation without cohesion, right? Because you guys understand what cohesion does, right?
Yeah, it's the alignment.
It's alignment, right? So if you had two vectors like this, after you apply the cohesion algorithm, the two vectors become like this, right? It's the average of the two. You don't really need that for a phase change simulation at the moment, right? Because you know, we don't really need that behavior. So either you can make it very, very weak, or you can switch it off in the flocking simulation. I would advise you in the beginning to investigate this. You start with a small number of agents, maybe like 5 or 10, and you switch off cohesion to see what happens, right? So basically, what we're talking about then is using the attraction rule and the separation rule, which is basically just attraction and repulsion, and the magnitude of attraction and repulsion, right? So what you've learned, hopefully by now in the flocking code, is what you can affect is the direction of the arrow, right? And you can affect the length of the arrow, right? Does that make sense? Like, what do you think is the difference between these two particles? The ones I just drew. What's the difference between those two? But what does that mean in the simulation?
Force.
How does that manifest? How would you see that in the simulation?
How is it related to water?
No, inside the flocking simulation, what's the difference? Yes, right? This one is fast and this one is slow, right? And if the vector is 0, it's not moving. Does that make sense?
Mm-hmm.
Right? So that's what you can affect in the simulation, right? You can affect the direction and the speed of a particle. That's all you can do in flocking. In the dumbest version of flocking, that's essentially what you're doing. Attraction points the arrows at each other. Separation points the arrows away from each other. Cohesion tries to make the arrows average out, so they start to move together. That's the genius of flocking, that just 3 stupid rules generate such an amazing simulation, right? And the other thing is, based on distances and things like that, you can decide how strong the attraction or separation is. So I'm just going to clear my screen, or can I scroll down, zoom out? Nothing. Okay. So if we look at phase changing as a process, you know, the definition of phase changing is it's a thermodynamic process, right? It's a process of dynamism based on the introduction of thermal properties. We can ignore the thermal thing for a second, right? So we can get the core concepts correctly. So if we just look at the concept of changing your phase, and phase is a principle of amount of motion in the body of agents, we're saying that you have 3 states. For the sake of argument, we're going to say ice, water, and gas, right? I think that's what you guys said, ice, liquid, and gas. Are those? Yeah. Right, and we know ice is slow, high attraction, and we know gas is fast, low attraction, and potentially high cohesion, right? You don't really need high cohesion, but if we don't have high cohesion, it will just become a mess, right? So maybe in gas you need cohesion, and then in liquids it's kind of medium, right? It's medium speed, it's medium attraction, and kind of low cohesion, right? So actually this is probably low cohesion and this is high cohesion, I would guess, right? So that's how you kind of convert these 3 states into the world of the flocking simulation. You see what I mean? And by making cohesion very weak, you won't necessarily have to get this flock that's moving around all the time. You know, you can get something that operates like ice. It won't look like a snowflake, but it's what Ola was trying to show us in Maya, right? Which is this particle cloud that is highly attracted to each other and starts to move very slowly and does not want to change its links, right? Once a particle is connected to another one, it doesn't want to break away from that. So there's a really high cohesion and a really high attraction rate without them self-colliding and all of that kind of stuff. And you can reduce the interparticle radius of collision, right? So that's also what you can do in flocking, which is the observation radius of the particle when it's looking for its neighbors, right? So you know this diagram from flocking, right? It's the area it looks for its neighbors. You can make that smaller, right? So in ice, it's looking at less, and in gas, it's looking at more potentially, right? So it's very easy to talk about changing between these. First of all, trying to run the simulation just as a single state, right? By changing the initial variables, and then the game is, can you change the variables during the simulation to move to phase change from one state to another, right? You see what I mean? And then to truly make it a phase-changing thermodynamic process, we would add a variable that doesn't currently exist in flocking, which is temperature, right? And you know that will be introduced by adding a variable which each particle holds, or it will be something in the environment, right? But we could say for now, for the sake of simplicity, it would live in each water particle. And if you have a high temperature, you tend towards gas, and if you have a low temperature, you tend towards ice. And then the interesting thing will be how that temperature moves throughout the particle field. And that's what causes phase change, right? As temperature variable navigates the population, you're starting to see the particle properties change, which means they change between ice, liquid, and gas due to the introduction of a simple variable like temperature moving throughout the population. Or if temperature is a facet of the environment, which we can do in a flocking simulation, you just you'd have to introduce something like a voxel, honestly, right? Which is a grid in which maybe a 2D grid or a set of dots, which the particles read based on their proximity. And then they're deciding, okay, I'm in a hot zone, I'm in a cool zone. And again, that affects their phase change. But that's why I'm saying it's easier just to have temperature as part of the particle set. Part of the initialized variables of a particle. So I think we can start without temperature first and see that we can control a flocking simulation to the extent that it stops becoming flocking and it becomes a particle simulation based on the same variables and the same set of algorithms, right? Which is attraction, separation, and cohesion. Just by editing the variables based on the phase. And then the next state is we can actually change the simulation from one state to another. And then the third step is introduce the variable that causes that change. You see what I mean? And then we can start to really explore scale, you know, and see like, okay, can we actually add, you know, hundreds of particles, change the attraction rules so that we can get something that starts to have some geometric patterning similar to ice, for example, right? And can we start to introduce higher cohesion rules and vector rules to get something that flows like a liquid? You see what I mean? And again, the point here is not to copy water, but is to produce this computational system that has a very clear rule set that you got from something else. In this case, the phase changing of the liquid materials or water molecules. And we've abstracted that into a set of simple particle rules and potentially a disturbing variable like temperature. And then we would use that to launch into the next step of the project, which is to say, okay, what does this particle cloud represent? Are there multiple particle clouds? Similar to what we were talking to in the other team, what becomes the objective of this particle cloud, right? So in their world, there was the element of conservation of energy. What would it be in yours, right? So that's something to think about and explore, right? Like, once we're able to build these high population phase-changing elements based on local introductions of temperature, what becomes the objective of such a system? What does it try to optimize for? In other words, right? What are you trying to optimize for? And we don't know, but that could be a really interesting thing to figure out, right? And then we can add some of your other ideas, like maybe it's about something navigating that particle cloud. Maybe it's that particle cloud navigating something else. So it needs to do different things, or maybe it's none of that. We just don't know yet. But I can see the next 4 or 5 steps very, very clearly for you guys, right? And again, I think you should render your particles based on their properties, right? Which is maybe the attraction states and the length of the vector change the color of the variable, so you can start to see who's in what phase, right? So you can set limits. If you're in this zone of variables, you're in ice. If you're in this zone of variables, you're a liquid. If you're in this zone of variables, you're a gas, right? So basically, if you're low attraction, so attraction equals 0.1, you're in a gas. If ice and if attraction equals 0.9, you're ice, right? And you just have 3 colors. So we can start to see this thing changing. You see what I mean? So it starts to become a simulation diagram, which is what we want. And then we can start to think about scales of simulation. We can start to think about, for example, an iceberg. Not that we want to create artificial icebergs, but an iceberg is just a large-scale ice simulation, right? So how does that happen, right? It will happen because you have this incredibly large liquid particle agent population, which is converting into ice in a different fashion that starts to create 3D structures, right? So that's the kind of stuff we can start to simulate, right? So, that could be an objective, which is to go towards static states, right? So in the end of the day, ice doesn't represent ice for us, but it represents static geometry of the population, right? Because these slow, high cohesion, high attraction populations, if you hit the ultimate limit, they stop moving, right? So you can see how you can go from a highly fluctuating population into a static geometric state of agents, right? Which is gas to ice, but we're not really saying this is made of ice necessarily. We're just saying this is how you create 3D geometries in this simulation.
Yeah, like
you see what I mean?
In general, it's like there's no need for it to be so direct. Like the water as a term has just been used as an abstract way to kind of jumpstart the conversation. But what the real interest is this phase-changing property, and whether it actually corresponds to like gas, liquid, and ice as like actual, things that we experience in the natural world or not doesn't really matter. It's just about the molecular structure being different between these 3, and there's like a physical outcome to that, whereas something is hard, something is like gaseous, something is liquid, and like has certain physical properties. So like don't think of it as water. Like it doesn't have to be water. It's just what jump started the conversation on phase changing. And if you really think about like the difference between like a flocking system and a particle system, is just the particle system has these ideas of cohesion and separation, but it doesn't have alignment. So particles bump against each other, but they don't really inform how they steer. There's no steering, whereas the flocking system has also the added value of steering. So if I can just share my screen for a second.
Yeah, let me stop sharing.
Yeah.
So basically, like alignment wouldn't be in our, let's say, the rules of making the simulation.
So this is what I'm saying. I think you can try it. I don't know, but I think it will generally be low. So like we said, you could argue that in ice there's high alignment and in gas there's low alignment. But in general, I think alignment should be weaker than the other 2 forces at all points, right?
Mm.
But you can have like high alignment, low alignment, but the range is like 0.1 to 0.4, while the range of the others is 0.1 to 1. You see what I mean?
Yeah.
Yeah. But you can also try it with no alignment and see what happens.
Yeah, so I think like in Maya, what you're limited to is this kind of, repel and attract. There's no steer. But even like in very simple terms, like this indicates a phase change for me in terms of how things pass from one state to another. and also like the search distance can also change, as well as the repulsion. So it's like, I think your simulation should start looking somehow. I mean, this is obviously like nonsense because it's like just a mess. But the idea is that it passes between these like hard states. Like I would identify this as like a hard state, and then goes back to, let's say, a dissipated state, which is a gaseous state, where things start looking a bit more, dispersed. So I think like what you're missing here, what flocking essentially has, is also steering, because it's just like stuff bumping against each other. There's no, intelligence beyond that. But the field of distance is what actually can, inform how this interacts further with each other, because they can maybe call to elements that are far further away.
Mm.
But this is what I think we should be looking at as in terms of just phase changing. That something is a clump, or something is like almost like a cloud-like agglomeration, because of the forces that bind them together, which can be tweaked, and you can obviously affect whether they repel or attract, how far can they see, quote unquote, and stuff like that. So I think like varying this kind of stuff is what you should be looking at.
Yeah, like a lot of your early simulations, I think, will be fairly simple, but also they have to be super clear.
Yeah.
So that's why if there's a combination of Maya and the simulate flocking, like I think flocking is your ultimate tool here. I don't want to really call it flocking, because you're just going to use the base code of the flocking, but the logic won't be flocking. Yeah. But that kind of assess and steer, or check your neighborhood and steer simulation will give you the ultimate control, and the particles will give you a really fast way to prototype, right? So I think that's the way you should think about it. The particles will allow you to prototype really quickly. And then the steering algorithms will allow you to get a lot of control of what you're trying to do, right?
So yeah, you're right in the sense that there's also like a, oops, I think I chose the wrong one. There's also like a MASH node that deals with flocking in particular.
Yeah, I tried using the flocking using MASH, but it didn't work. And
you can try, like maybe there was something in the setup that wasn't working properly, but you can always try from like the content browser in MASH examples. There should be one that's just flocking.
Yeah, it's I think it's at the top.
No, this particle trace.
I think it's at the top, the first example.
No, this is a longer curve. There's one more. I just had it a second ago. I don't know which one it was. Call off flight trails.
So like how will this, like if we did this on Maya, how would it help us, since we can't control it?
You can only do it with Python and Maya, because you can add a custom Python node to it. So if someone has Python scripting capabilities, you might be able to tweak it further. Yeah. You can also connect it to a particle cloud, because MASH has that ability to connect to a particle.
Like if you guys are comfortable exploring it in your Unity code, then go there and just use the particle stuff, not to copy flocking, but just to explore some principles. But yeah, like your project, you need control of the variables. Like there's no way around that. So, if that means you all have to jump in on the Unity code, go for it. But I think like the first steps are fairly simple, right? We're not trying to add anything too complex. It's literally just the attraction, cohesion, separation variable.
So like these you can definitely affect from here. It's just that they're applied crushingly to all the agents. So if you can unlock this and try to vary that might actually be more useful, because you can affect these things, obviously, right?
Yeah. So this kind of stuff, like in Maya here, like this, it can allow you to play with the variables very quickly and see what will happen. But in Unity, because you're controlling the code, you can really have control. And I would start with very like structured setups, like grids and stuff like that, not like random distribution of particles. So you can get some repeatability in your experiments.
Okay, so like, this is great, because I think it intuitively gives you an idea of how this works, because you can just like work with sliders and see what happens, which kind of helps. But in general, I think I would agree with Mustafa that the ultimate intent is to move into Unity because you have more control there. The other option, yes, is that a MASH does recognize a Python node as well. So if there are Python coders, maybe someone who's working with Shadia, you can also add a custom Python node.
Okay.
Yeah, but yeah, like in the end of the day, like when we want to add temperature or any variable like that, that's going to have to be in code, right? So in a controlled fashion.
Yeah.
So yeah, use the particle or these kind of nodes as prototypes, but use the code as your kind of development environment.
Okay.
May I ask a question? I think that this conversation about flocking is basically this flocking thing is helpful regarding the distribution of molecules of water in its phase. So if we want to move on to the next step and try to see how we can move to the phenomenon part, should we introduce them? Can we combine that, for example, with a growth simulation? Can we combine that with another strategy? Because I feel that the distribution logic, which has the flocking system, it might be very it might limit us in a way. I don't know.
What do you mean? Like, why would you need a growth system?
For example, I think that ice is very much related. Snowflake is for sure related with the growth system.
Yeah, but this is because you're thinking of a snowflake. So a snowflake is a structure that looks like a growth system, right? Like we're only talking about ice in terms of like it had strong bonds, it keeps stuff together, it doesn't vibrate. We're not saying, oh, it looks like a snowflake. I think like all of the names you set out, like I think it was like iceberg, wave, or whatever. These are great for nomenclature, especially for structuring your presentation so that people can kind of relate terms to a certain thing that's happening within your project. But I don't think it actually relates to a computational model as much as you think. I think the computational model is extremely simple in what we just discussed with Mustafa right now. You don't even need all this nomenclature to explain the computational model. You need nomenclature to explain the project itself. Yes. So don't think of it that way.
So,
yeah, like for example, the easiest way to generate a snowflake is using cellular automata, right? Like Game of Life. That's the easiest way to generate a snowflake diagram. But that just looks like a snowflake. It doesn't behave like a snowflake, right? That's the problem. You were trying to produce long-term behavioral systems. So, if you want to, we can look at how you can take the system and try to create more kind of rigidly structured populations from it. But yeah, I would argue that's about like kind of locking particle attributes in a certain way. Like, once you achieve a certain level of cohesion or attraction, you can lock a particle in a certain geometric fashion, right? And then you could get like this kind of fractal system, which will behave more like a snowflake. And then you can break those bonds and go back to the liquid state, right? But you can't do that in a cellular automata system, because a cellular automata system uses a game of life that, I think there's a snowflake rule, which will produce something that looks like a snowflake, but has no behavioral resemblance to the snowflake. You see what I mean? And that's why I'm saying, like, that's when the analogy becomes detrimental for you guys, because you try to simulate the physical qualities rather than the behavioral quality. And with a good computational model, that you were trying to simulate the behavioral qualities of the system. So I wouldn't say we're going to go down the route of a growth model, but we can go down the routes, once you can control this, of a model where you further control the particle relationships to produce these kind of, in the case of a snowflake, kind of fractal-like geometries, but you can easily move back and forth between that state and any other state in the phase change network. You see what I mean? So I actually think you're using a system that's incredibly non-limiting, right? Like particle flocking is a very open system. I doubt you'll be limited by it, right? Like it's more if you go down L systems and stuff that you get limited, because there's very little you can do with an L system actually after a while, right? Like basically you edit its number of splits and the angle of split, and basically that's all you can do with an L system. But with kind of agent-based simulations, which is what you have, you can do whatever you want, right? And add any amount of intelligence. So I think it's actually an incredibly unlimited system. But you just need to get the basics right, which you still don't have.
If it's okay to share one slide, I think we have a try about this one.
Yeah.
For this, we use the L system to simulate the point growth with certain like growth system. Mm-hmm. It's kind of simulate with the ice spikes because it's growth in a kind of same logic.
Yeah, no, I understand, but again, like it's too literal. Like we're not trying to emulate the spikes of ice. We're talking about ice in an abstract sense, right?
Okay. Yeah, like we're talking about ice as a one state of a phase change system, rather than trying to make ice. So to me, this is better, right? Like, you know, because I can see, I can argue that on slide 16 or whatever that number is, 167. That, you know, the area of large particle radii is ice and the area of small particle radii is liquid, right? But I know that particles are not behaving differently there, right? Like you want those big particles to be just not moving. And I think this is what you can do with a particle simulation or an agent simulation we just discussed, right? Because then all you would do is say the radius of the agent is dependent on the motion vector. So the larger the motion vector, the smaller the particle, and the smaller the motion vector, the larger the particle, you would get this diagram, exactly this diagram, right? So that's why I'm saying, like, if you use an agent-based model, like it's what I was saying, Daphne, you're actually not limited at all, right? You can do a ton of things. It's these other geometric systems like L systems and stuff. They produce complexity very quickly, but that should give you a clue that you're going to get stuck very fast with these kind of tools.
Okay.
Exactly. So the state of a phase change, which maps to a set of variables in an agent simulation. Yes, all of your simulations are based on simple variables of an agent system that can be abstracted to the phase change process. Yes.
Yes.
Right. So first you're trying to achieve just the single state. You're trying to make gas, you're trying to make liquid, you're trying to make ice, and then you can move between the three, right? And then you can have multiple states existing in the same population, like that slide 167 you were just showing. And then you can add temperature, which starts to become the environmental condition that affects the population, right? If we think about it abstractly, that's all that means. And then you can start to do stuff with the geometry or the geometry of the agent to start to add three-dimensionality to the population. You can start to add constraints of how particles connect to each other when they get really close to create more fractalite systems, etc., etc. So there's a ton we can do again, but if you don't get this right, we'll be building on a bad foundation. That's why we're saying really focus on trying to achieve the gas state, the water state, the solid state, and then try to move between them as a change of variables. And that is what phase changing is. But again, I think this is way clearer than yesterday, than last week. I think you're moving in the right direction. I think flocking is the perfect system for you. And by next week we should stop calling it flocking. It's just your agent-based models. Yeah, I think that's the right direction. Okay.
Good.
All right. Let's move to team, which is air, right?